Hey guys, Mr. Riz here to help you out on the 3.7 notes. So 3.7 is all about optimization. And a lot of these problems are going to be involving using derivatives on story problems and trying to find mins and maxes. So things we've done before, but specifically just like, real life scenarios or things like that. So a lot of these problems you can see would be like if you were an engineer or working for a company, trying to design something that would maximize the shape of something, but still minimize the cost. And so those are going to be things that we do throughout this. This video is going to be a little bit longer, so feel free to break this up into chunks. I'm just going to go through all the problems in the notes because basically this section is just a ton of different story problems. There's no one type of story problem that build off of each other. It's just there's a lot of different scenarios that can happen. We're just going to go over a bunch of individual ones. Okay, so first problem here is we have this cardboard box here that is 14 inches by 10 inches. All right, we're going to cut out the corners. So we're going to take this X or H out on both sides and fold up the edges so that we have a box that has no top. Okay, determine the height of the box that would give the maximum volume. Okay, so what we always want to do is, go through and probably start an equation out. What are we trying to maximize? All right, the thing that we're trying to maximize is the volume. All right, that's important because we're going to find the maximum of that. And so we're going to have to take the derivative of it later. Hopefully we know that the volume of anything, of any rectangle prism would be length times width times height. Okay, so now could we go through and put this in terms of a single variable? And they use H here. For all purposes, I'm going to use X. I think it's going to be easier if I just understand H is equal to X. The length we'll say is 14 minus 2X. Because we took the whole length is 14, but we're going to cut off an X here and X here. And so that's what this part is. And then the width would be the same thing here, but it's 10 wide, so 10 minus 2X. All right, so let's see. The volume equals the length is 14 minus 2X. The width is 10 minus 2X. And then the height is just X. All right, so whatever we plug in, so if we determine, if we want to cut out 2, we can plug 2 in for this, and we can figure out the volume. If we want to use 3, we can plug 3 into this, and we can find the volume. Now, if we want to go through and find the maximum of this volume, we'd want to go through and find the critical number on the derivative. Okay, so before we jump in to take the derivative, let's see if we can simplify this expression at all. So we can distribute this 14, we can FOIL this out and then times it by X. And so let's see, if I times 14 by 10, I get 140, and I'll times it by X, that's X. All right, 14 times 2X is a negative 28X, and then times it by X squared. All right, negative 2 times 10 is negative 20X, but then we'll times it by X, X squared. Negative 2 times negative 2X would be a positive 4X squared, but we'll times it by X and make it X cubed. Okay, so the volume formula we could just rewrite as 4X cubed, and then we got, let's see, that'd be minus 48X squared, and then plus 140. Okay, so if we want to find the critical points of this, the derivative or the mins and maxes of it, we have to take the derivative. And this is a lot easier to take the derivative of than this. They're the same function, but, this one we'd have to do the product rule a couple times. All right, so let's see, 4X, that goes to 12X squared. Minus 48 becomes minus 96X. And, that should be, just notice this would be 140X. And this makes 140. Okay, what we need to do now is to figure out when does the derivative equal 0. Okay, so we have a quadratic. Anytime we have a quadratic, we try to factor it. We can make our life easier by dividing this all by the same number. I don't think 140 divides by 12. Well, can we divide them all by 2? 2 and 70? Can we divide them all by 4? I think we can divide this all by 4. I don't think we can really do anything more than 4. I'm just going to take out a calculator right here, double check that. So let's divide everything by 4. Since we set this equal to 0, this would be a 3x squared. 96 divided by 4 is 24. And 140 divided by 4 is 35. Okay. All right. So I just made that simpler trick we can do. Okay. We still have a quadratic that we got to try to factor.
Attention staff, I realize many of you have already taken attendance. If you do have students that come to your class now, just make sure to let Mrs. Wright know that they arrived so she can fix that. We did have a late bus show up that we were not expecting, so we had to just go ahead and hold attendance and send everybody for now.
Cool, thanks. All right, so we can always try to factor. If not, we can do the quadratic formula. In this section, we're going to have to do it a lot because realistically, these numbers are not going to come out perfectly. So we got x equals negative b plus or minus the square root of b squared. Okay, what's 24 squared? 24 squared is 576. Minus 4 times a is 3 times c is 35. All over 2a, that'd be 6. All right, so we got 24 plus or minus the square root of, all right, what's 576 minus 4 times 3 times 35? Plug that in the calculator, that's 156 all over 6. Okay, so we could break this down, get an exact answer, but let's just go through, get the 2 decimal approximations here. So what's 24 plus the square root of 156? And that's like 36.6, and we'll divide that by 6, and we get 6.08. We get a little bit more, but that's what we get. And we also need to do 24 minus the square root of 156 and divide that by 6. And that we get 1.92. All right, so we have 2 answers here, and we got to go through. Now, keep in mind, when we get a critical point of the first derivative, that's a minimum or a maximum. We want to find the maximum. So what we need to do now is we just need to take our critical numbers that we have, and we're going to plug them back into our function. Okay, we can plug it into this one or that one. Okay, so I'm going to go ahead and I'm going to plug in, you know, the first one. What's the volume if we plug in 6.8, which might end up making sense here. So if I plug in 6.08, so 14 minus 2 times 6.08 times 10 minus 2 times 6.08 times 6.08, we get a grand total of a negative 24.16 volume. Okay, that's weird, but if we think about it here, if we are taking away 6 inches off of both sides when it's 10, yeah, that's not going to happen. So that is definitely not the answer. Let's just double check that the volume of 1.92 works out. So here we go. What's the volume? So we're going to plug that in. What's 14 times 2, or 14 minus 2 times 1.92 times 10 minus 2 times 1.92 times 1.92. That comes out to be 120.16. All right, so that's lower, that's higher, that's the min. Here's our max.
Staff, if you haven't taken attendance, then go ahead and do so now. We'll go ahead and start marking kids, tell you they're coming in the building. Thank you. Have a great day.
Okay. There we go. Sorry about that, guys. Well, we'll keep going through this. All right, next, we have a printer needs to make a poster that has a total area of 200 square inches. And we'll have 1-inch margins on the side and 2-inch margins on the top, and 1.5 margins on the bottom. Okay, so let's draw that out. Let's kind of see what's going on. So we got to have this poster here. It's got to have, you know, the poster goes in the middle here, and there's got to be 200 square inches. What we also know is that there is a 1-inch margin on each side. There's a 2-inch margin on the top and a 1.5 margin on the bottom. What dimensions will give the largest printed area? Okay, so actually, is that what we want? What dimensions with the largest? Oh, the poster will have a total area. Okay, you can make a poster that has a total area. Okay, so this is what we want to, it's not 200 is in this area here, that the overall area of everything has to be 200. All right, so what do you think about this here is that we have this printed area that is like a rectangle. It's X by Y rectangle, right? That's what we want to maximize. Our area we want to maximize is our x times y. Well, what we also have to do sometimes is we got to look for constraints that we have. Because if we take the derivative of this equation, area prime, we'd have to take the derivative with respect to x and then also take the derivative with respect to y. And that's difficult. But what we can do here is to look, maybe we can change some of this information up to replace maybe the x with a y, or maybe change the y to an x. So let's see. If we know that the area of this whole thing has to be 200, we can look here to see that the area, like going up and down, would be, let's see, it's y here, but we would have plus 2 on the top and plus 1.5. So this top to bottom is y plus 3.5. And then going left and right, we have an x plus or 1 plus an x plus another one, that'd be an x plus 2. So if we go through and multiply x plus 2 times y plus 3.5, we have to make this equal 200. So my goal here, or our goal, is let's get this y by itself, so then we can replace it in our area problem. Okay, so that means y plus 3.5 would have to equal 200 divided by x plus 2, right? Because all we got to do is divide that over. There we go. And then we can say that y equals, well, 200 over x plus 2 minus 3.5. Okay, so that's something we can replace that with. So we can say the area is x times 200 over x plus 2 minus 3.5. Okay, so when we go through and take the derivative of this, we could do the product rule, or, can we rewrite this equation to work this out? We can distribute the x and say the area is 200x over x plus 2 minus 3.5x. Okay. We could do the problem as is. We could take the derivative of this. If we leave it like this, we'd have to do the quotient rule, do all that, and then off to the side to have the derivative of this. Or we can try to combine these together using the product rule. I just think, let's just leave these alone and let's do the derivative as is. All right, so quotient rule, we got low is x plus 2, d high is 200, then minus high is 200x, then d low is just 1 over x plus 2 squared. So there's low d high minus high d low over low low, and then we also have this guy hanging out at the end, and then we'd have a minus. That just becomes 3.5. All right, so let's look at our derivative. If we distribute the 200, we got 200x plus 400, and then minus 200x all over x plus 2 squared, and then minus 3.5. So our derivative here would come out to be 400 over x plus 2 squared minus 3.5. So there's the derivative. What we need to do now is set the derivative equal to 0, because that's where we find any critical points, any mins or maxes. All right. So what we can do here is just move that 3.5 over to the other side and figure out, when does 400 over x plus 2 squared equal 3.5? Well, we can go through and cross multiply and divide here and figure out, okay, so if I do 400 times 1 divided by 3.5, that's what x plus 2 squared has to equal. So I'm going to do that real quick, just in the calculator. 400 times 1 divided by 3.5, or just 400 divided by 3.5, is about, oh, that's not nice, 114.29. Next, we need to get the x by itself, and we could divide by, or take the square root, not divide. Now, when we take the square root, we get a positive and negative answer. But realistically here, x is never going to be negative. That wouldn't make sense here. So let's take the square root of that answer. And we get about 10.69. Oh, and that's not what x equals, but that's what x plus 2 equals. And then we could subtract 2. So we would get finally here x equals 8.69. So it does say what dimensions give the largest printed area. So we have to kind of do a little bit of work to get the dimensions. And I'm assuming the dimensions are talking about the entire printed part here. We could talk about specifically the dimensions here on the inside here, which is 8.69. But let's go through. If we know the bottom of this printed area here is x plus 2, so the x is 8.69. The bottom of that would have to be 10.69. And then let's go through and go back to figure out what y is. We know from way back here that y is 200 divided by x plus 2 minus 3.5. So we can take 200 divided by that 10.69 and then subtract 3.5. And so this is what y is. Y would be 15.21 just about. And so that means this area here, if we add 3.5 to that, this would be a 18.71. Now something that you might want to do here, 18.71, is to, just double check that these work out. If we multiply that number by 10.69, we get 200. So the area still works out to be 200, and we just figured out that this area in the middle here is maximized. So you can see a lot of these problems here, we just really need to trust that we know the derivative. I mean, we can go through and plug different numbers in one at a time, but we just got to trust the process here. The more that we do, the easier that this becomes. So feel free to, pause the video at any time, start this video, try to do some problems on your own, and then come back to this. All right, we need to enclose a field with a fence. We have 500 feet of fencing material, and the building is on one side of the fence. It doesn't mean, okay, so what we got going on here is we have a building. This is the side of a building, aerial view, and then we have some fencing. We're gonna make like a rectangle fencing. Okay, we got 500 feet of this fencing here, and we don't need to put any up against this building. Determine the dimensions of the field will have the largest area. So when we make this rectangle here, we have this x and y, and that's what we want to maximize, right? X times y. So we don't want to just take the derivative with straight up x and y. We got to have a constraint. The constraint that we know is that all this area here is 500 feet. Or not area, but all the fencing length is 500 feet. So if we think about this here, we have two x's and one y. So 2x plus y has to equal 500. So we can go through and get y by itself, like we did in the last problem. This one comes out to be a little bit easier. We can say y equals 500 minus 2x. Okay, so whatever x is, y would have to be 500 minus twice of that. So if x is 100, y would have to be 300, because it'd be 300, 100, 100, that's 500. If x is 50, y would have to be 400. So we can go through and see the different shapes that we can make here. So now let's take that constraint and plug it into the equation. So the area that we're trying to maximize is x times y, but really it's going to be x times 500 minus 2x. We could take the derivative as it is, but it'd probably be better to distribute it out like we did in the first problem and the second problem. So we have an easier problem to take the derivative of. All right, so let's take the derivative of that.
Good morning.
Morning. All right, the derivative of 500, x is 500. And the derivative of negative 2x squared is negative 4x. Remember, any derivative, we're going to try to set it equal to 0 to find the minimums or the maximums, the critical numbers. So what does 500 minus 4x equal 0? Well, that's when 500 equals 4x, or when x would equal 500 divided by 4 is 125. So it does say determine the dimensions, and we can call this, the width, and that's the length if you want. But basically, we're going to go through and say this is going to be 125 by, and then we just got to plug that in. So what would be 500 minus 2 times 125? What's 500 minus 250? That'd be 250. Okay. So you guys can see that problem wasn't too bad, but we went through the same process steps. And you see, like, A lot of these problems are going to be all the same steps where you set up what you want to maximize, you find or use your constraint to get the equation down to one variable. Once it's in one variable, you take the derivative, set it equal to 0, and then you plug everything back in. All right, we want to construct a box whose base is 3 times its width. The material used to cost the top of the bottom is $10 per square foot. The material used to build the sides is $6 per square foot. The box has a volume of 50 cubic feet. Determine the dimensions that will minimize the cost of the box. Okay, so if you remember this problem came from the stand and deliver packet. And this was one of those AP questions here. All right, so let's draw this out here. We have a box. That's a terrible looking box. All right, so we have like a bank length, width, and the height. All right, so we have a lot of different things about here. We know a couple things, and we're going to start using some constraints here. We know that the base length is 3 times the base width. So I'm going to just call this X, and that would have to be 3X. The material used in the box costs $10 per square foot and $60 on the side. Okay, so $10 for the top and $6 on the sides. And what else? Well, the volume has to be 50 cubic feet. All right, so volume, which is typically length times width times height, we now know, okay, so that's got to be 50 equals, the length is 3x, the width is x, and we don't know the height. But we can go through and say, okay, well, 50 would have to equal 3x squared times h. We can figure out that the height would have to be whatever 50 divided by 3x squared is. Okay, so now what we have here is basically the width is in terms of x, the length is in terms of x, the height is now in terms of x, and we can go through. What we actually want to minimize is the cost. So the cost of the box is all the areas of each side, add them together. So let's see, let's talk about the top and bottom. The top is the width, which is x, times the length, which is 3x, and then times the cost of it, which would be $10. And so there's the bottom of the box. Now the bottom would be the same as the top, so we can times that by 2. Okay, so there's the cost of the top and bottom. All right, now let's get the front and back. The front is a width of x, a height of 50 over 3x squared. So that, you know, building this rectangle here. And its cost is $6. And we can times that by 2 because there's a front and a back. And then we got to do the left and right as well. So the left and right, the one part is 3x. The other side is 50 over 3x squared. And it costs $6. And there's a left and a right, so we can times that by 2. All right, so here's our cost formula. Piece of cake, just take the derivative of it. Now, okay, we definitely want to go through and let's simplify this. All right, x times 3x times 10 times 2. What is that going to be? What's 3 times 2? 10, that's 30. So this would be 60x squared. All right, what's going to happen here? All right, what we have, this might be easier to think of this as 50 thirds times x to the negative second. All right, so let's go through. What's x times that times 6 times 2? Okay, I'm going to just on the calculator. 50 divided by 3 times 6 times 2 comes out to be 200. And then x times x to the negative second becomes x to the negative first. All right, and then we'll do the same thing here too, because that's the same thing there. All right, so what's 50 divided by 3 times 6 times 2? That's 600. And then we'd also have an x to the negative first. So we're still not, we can actually make our costs a little bit easier here. The cost would be 60x squared and then plus 800x to the negative first. Okay, so now we got it simplified. It's all in one term. It's all in x. simplify here, we can take the derivative. So what's the derivative of the cost? Well, 60 times 2, that's 120x. And then, okay, here what we got to do is 800 times -1, which is -800, and drop that down to the -2nd. So we want to now figure out, okay, when does that equal 0? When does 120x and then minus, let's make this 800 over x squared, because that's what x to the -2nd means. When does this equal 0? Well, we can move this over here and say that's when 120x would equal 800 over x squared. And we can put this over 1 and we can cross multiply. So 120x times x squared is 120x cubed. When does that equal 1 times 800? 800. So when does x cubed, if we take 800 and divide it by 120, 800 divided by 120 would be about 6.6 repeating. Well, you know what, we'll do 6.6 repeating. And then we could take the cube root of that. The cube root, we don't have to worry about positive or negatives. All right, to the third power. The cube root of that would be about 1.88. Okay, so that would be the width, right? Because that's what x is. So let's go through and let's start making our dimensions. And it might be easier to just start labeling, okay, what's the width, what's the length, and what's the height. Okay, so we know that the width is x, which is 1.88. The length, we could times that by 3, because the width, so we'll just times that by 3. We get about 5.65. And then the height is 50 divided by 3x squared. Okay, so I'm going to take our 1.88 and I'm going to square it. And I'm going to times it by 3. And then I'm going to do 50 divided by that answer. All right, and we get about 4.72. There we go. So there's the dimensions that would reduce the cost of the box. What we might want to do too is just, we got these numbers here, might be kind of confusing where they came from. If we want to just double check, okay, what's 1.88 times 5.65 times 4.72, just in the calculator, 1.88 times 5.65, forgot the decimal point there, times 4.72. All right, I get 50.13. Okay, so remember our volume was supposed to be 50. These are all just decimals that rounded, and because they rounded, we're just slightly off. If we probably used more decimal places, that number would have been even closer to 50. Okay, I'm just going to kind of keep going on here until we start getting comfortable. All right, we want to construct a box with square base so that we only have 10 square meters of material to use for the construction of the box, assuming the material all being used to determine the maximum volume. Okay, so we're going to make a box that has a square base. So both of those sides are x, and then we have this height here. So just like the problem we did, this might be a little bit easier to do. We know that we want to find the maximum volume, right? So the volume is x times h. We probably want to change this h so we can maximize the volume. All right, we know that the surface area of all the box has to be 10 square meters. So if we think about the surface area would be, let's see, we have an x times x would be x squared. We'd have 2 of those. And then we would have 4 of these x by h's. And that would have to equal 10. All right, so can we get this h by itself so then we can plug it in over here? So let's see, that means 4x times h would equal 10 minus 2x squared. So the height would be 10 minus 2x squared over 4x. Okay. We could probably reduce that, but let's just leave it like that. Let's see what happens here with the volume formula. So the volume formula is, well, x times x times 10 minus 2x squared over 4x. And we can probably simplify that a little bit. If we multiply this x times the 4 over x, that kind of cancel each other out, right? So the only thing we need to do is distribute that. And the volume here would be 10x minus 2x cubed over 4. And we probably, since this is just a 4, we can divide these out, maybe put fractions if we want. 10 divided by 4 is 5 over 2x, and negative 2 over 4 is negative 1/2 x cubed. Okay, so now what we need to do is take the derivative of this. We take the derivative of this, 5 over 2x becomes 5 over 2, and then minus 1/2 times 3 is 3 over 2x squared. So we want to find the critical numbers of that derivative. To find any critical number derivatives, we're going to set it equal to 0. So let's move that over to the other side. So we get 5 over 2 is equal to, I'm going to make this 3x squared over 2. We can cross multiply like we did before. We can get, 3 times 2 would be 6x squared equals 5 times 2, 10. So x squared equals, if we take 10 and divide it by 6, that's 5 over 3. And then x would just be the square root of that. Now, technically, we get a positive or negative, right? But realistically speaking, we can never have a negative side length. All right, so what's the square root of 5 over 3? The square root of 5 over 3. Now, if we wanted to, we could put like radical 15 over 3, I think is the correct answer. But square root of 5 over 3 decimal-wise is about 1.29. All right, so we're going to go through and determine the dimensions. What's the width? What's the length? And then what's the height? So the width would be 1.29. The length would also be 1.29. It is a square base. And then the height, we'd have to go back and use this formula here. Okay, so what's 10 minus 2 times 1.29 squared? I think that's 5 over 3. All right, over 4 times 1.29. All right, so let's just do the top here. What's 10 minus 2 times 1.29 squared? That turns out to be 6.67 divided by 4 times 1.29. That's 5.16. If we divide those up, we get up crazy 1.29. Think about that. That's some nice logic there. That ends up being a cubed. And so we'll find some of these weird properties that are going up. Some of the best properties out there are like squares. Squares have the largest volume with the lowest perimeter. Cubes are the same thing three-dimensionally. They have the largest volume given surface area of a prism. Now, sometimes we can change the shape and actually spheres are better, or circles. But there we go. All right, let's go. We'll probably have to break this video up into, actually no, we'll split the notes up, and after this, we'll do another video for help with the homework. All right, a manufacturer needs to make a cylinder that holds 1.5 liters of liquid. All right, so we got a cylinder going on here. So we have a radius and we have a height. Determine the dimensions, and we got to hold 1.5 liters liquid. Determine the dimensions that will minimize the amount of materials used in the construction. Okay, so that's not a lot of information, right? Well, the volume formula that we have is, actually, we don't want to minimize the volume, right? We want to minimize the surface area, right? All right, the surface area of a sphere, okay, we have a circle here, which is pi r squared, but we'd have one on the top and then we'd have another on the bottom. So we got 2 pi r squared. And then we have this side part here, which is the circumference, 2 pi r times h. So what we want to do here is to isolate one of these variables. We can either make the equation all r's or all h's. I would definitely say if we can change the h to an r, that's going to make our equation a whole lot easier to deal with. So let's look at the constraint. The constraint is that the volume has to be 1.5 liters. So what we can do here is we can take the volume formula for a cylinder, which is pi r squared h. We can set that equal to 1.5. And then we can get the h by itself. So h is equal to 1.5 over pi r squared. So you can see like every problem is going through, okay, set up the problem that you want to reduce or maximize. Okay, so we want to minimize this problem here. We look to see that there's multiple variables, and when there's multiple variables, we isolate one of them using the constraint. So we want to isolate this h here, so we use our constraint to find another version of that. So h was equal to 1.5. So now we rewrite the equation, 2 pi r squared plus 2 pi r times 1.5 over pi r squared. All right. What you probably want to do before you take the derivative is simplify that. All right, so 2 pi r squared doesn't change. Now let's see here. If we times the 2 times the 1.5, that's going to become 3. And then let's see. The pi here divided by pi goes away, and r divided by r squared makes an r on the bottom. So really we have 3 divided by r, or 3r to the negative 1 power. Now that becomes a problem we can take the derivative of. So the derivative of this, okay, 2 pi times 2 would be 4 pi. We drop the r down to the first degree. And then minus, well, 3 times negative 1 is negative 3, r to the negative second. Okay, so let's see here. That means we would go through and set that equal to 0. So when does 4 pi r minus 3 over r squared, we'll change that, equals 0. You guys have probably seen problems like this now. We're going to move that over to the other side. So when does 4 pi r equal 3 over r squared? So we're going to go ahead, cross multiply, and we're going to solve for r. When does 4 pi r cubed equal 1 times 3? 3. So if we go through, we can divide by 4 pi, and we're just going to plug that in the calculator. It's going to be really small. 3 divided by 4 pi. 4 pi. There's the pi button. Is about 0.239. I'm going to even just put 3 decimals down because it's pretty small. 0.239. And then we're going to take the cube root of that. All right, so we'll take that to the 1/3 power. And that means r would be about 0.62. Okay, so that means the radius of that cylinder would be about 0.62, and then the height, we got to plug that back into here. So what's 1.5 divided by pi times 0.62 squared? All right, so we'll square that, we'll times it by pi, and then we'll do 1.5 divided by that, and I get about 1.24. Okay. Which, if you think about it, kind of makes sense, because if our radius is about 0.62, that means the diameter would be, what, 1.24, and our height would also be 1.24. So we're turning that shape, even though it's not a, cylinder or a cube, into like a cube shape where the width all the way across is about the same as the height. All right, guys, so there we go. There's the notes. Well, I'll have another video to help you guys out with the homework, but if you guys have any questions, make sure you ask, and thanks for watching. Have